Here we'll cover another nucleophilic addition reaction to aldehydes and ketones. This reaction is acid catalyzed hydration. Hydration, we are adding H2O. Okay, and now this one's acid catalyzed. So this is different from that previous addition of hydrogen cyanide that we looked at. In the addition of hydrogen cyanide, we have a basic solution, pH of 9 to 10. When we have an acid present, acid catalyzed hydration, for example, the first step of the reaction will be a little bit different. So let's do an example with a general scheme. So example, and then reaction scheme. We'll use acetaldehyde we are adding water. I'm going to represent that as HOH. We have some acid present in solution. This is another reversible reaction. Now, the acid that's present could be sulfuric acid, it could be hydrogen chloride, hydrogen bromide. There are a lot of different options. As long as we have a strong enough acid for what's required in this reaction, we can have various acids present. The result of this reaction is, again, of course, addition to the carbonyl carbon. It is still bonded, that carbonyl carbon is still bonded to the hydrogen and the methyl group. It's bonded to the original oxygen, but now that's a single bond, and that oxygen has a hydrogen. And then that carbonyl carbon is also bonded to another OH group. So we have two OH groups bonded to that carbonyl carbon. For one of them, the oxygen was the oxygen that originated in the aldehyde or ketone there. This is called acetaldehyde hydrate. It's a type of molecule called a gem diol. The gem part communicates same atom, and then diol is two alcohol groups. Di for two, all for alcohol. So gem diol means we have two alcohol groups on the same atom, and that's what that acetaldehyde hydrate is. Okay, here's an example with a general reaction scheme. Let's go through the mechanism to understand what's happening here. So we'll start with acetaldehyde. Now, if we have water in solution with an acid, the acid will protonate the water molecule. Let's actually write that first. So let me erase the acetaldehyde here. We have water, H2O, present in solution with any acid, then we will have H3O plus present in solution. And so H3O plus is what we'll use to show the acid when we go through the mechanism. Okay, now we'll do the mechanism starting with acetaldehyde. From an earlier video, we discussed that aldehydes and ketones are weakly basic at the carbonyl oxygen. And so if we have a strong enough acid present in solution, that acid will protonate that carbonyl oxygen, and that's the first step of this mechanism. So when we have an acid catalyzed nucleophilic addition, the acid will protonate the oxygen. So oxygen forms a new bond to the acidic molecule. And this is a proton transfer, reversible proton transfer reaction, where the product side we have almost the same molecule. We still have that double bond between carbon and oxygen, but now this oxygen is bonded to a hydrogen. And then we have water. As the byproduct. Our oxygen is positively charged. This is sometimes referred to as an activating step. We are activating the carbonyl. Having that hydrogen bonded to oxygen there causes the oxygen to then pull electron density even further away from the carbonyl carbon. Oxygen is positively charged. It's sharing a lot of electrons, and it wants to own more electrons. It's more stable by owning more electrons. So the electrons in the pi bond between carbon and oxygen are even closer to the oxygen atom. And so the carbon has an even stronger partial positive charge here. That activates the carbonyl and makes that carbonyl carbon more susceptible to nucleophilic addition. Our nucleophile in this case is water. So the water molecule can then go bond to the carbonyl carbon and make the oxygen happy, give the pi electrons to the oxygen atom. The product here, we have carbonyl carbon still bonded to the methyl and the hydrogen. We have an OH group at the top now that oxygen is neutral. And then we have water bonded to the carbonyl carbon. This oxygen is now positively charged. And our last step here is to do a proton transfer between this positively charged oxygen and another water molecule. Now remember, in solution, we have our solution of water and an acid. So we have H2O present and H3O plus present. So when we protonate, like in this first step, we use H3O plus because that can give away a proton. When we are deprotonating, like in this last step, we use H2O because now H2O can gain a proton and form H3O plus, which is already present in solution. So this water will take a hydrogen, electrons go back to oxygen, and we form the gem diol product here. So carbonyl carbon still bonded to CH3, still bonded to hydrogen, bonded to the OH that we formed in the first two steps, and then OH down here, which we just deprotonated that oxygen. So now it is neutral. And here's that gem diol, and then we reform H3O plus, which can then be used in future reactions in this flask. So this is the mechanism and general reaction scheme that we talked about previous in the video for acid catalyzed hydration or adding H2O to an aldehyde or ketone.